So welcome back. Before we dive into 4.3, we are going to be taking a look back at something that was covered in one of the previous chapters, but really doesn't get used until the section that we're about to use. What's nice about this is that if you can recall from when we were reviewing with systems of equations, we had a few ways that we could solve these using one method in particular, substitution. An example where this would be used is where we have one equation that's already isolated, so y equals 4x. And we have some other equation that doesn't necessarily have a variable isolated, but we could definitely take it further. So it would make more sense to take 4x, put it in for y, solve from there. We've also seen elimination, where we may have to modify an equation, or if we see that we have terms that are opposites of each other in a system, like a negative 2x and a positive 2x, it sometimes makes more sense just to follow through and eliminate one of the variables and solve for the other. We also see linear combinations where, although we may try to use substitution or elimination, a linear combination is where we modify one of the equations to eliminate some type of variable and go from there. As we work now with three terms, that's pretty much the main change in this section, is that now we're working with x, we're working with y, and we're also working with z. So we're working in 3 dimensions now. As seen here, they go over a visual of what this looks like in the context, saying that we can have a system where there's no solution, so no point lies in all 3 planes, the x-plane, y-plane, or z-plane, so 3 dimensions, notice. We may have one solution where there's only one unique intersection for all of those planes, x, y, and z, or infinitely many where we could have an infinitely number. We could plug in any type of number and have some type of outcome there. That's kind of a rare occasion. But again, what's nice is that for this, we definitely use a lot of our prerequisite knowledge of elimination and also substitution to take these down, solving this system with now again 3 equations and 3 variables. We will have to use one of the equations more than once, so notice that we have 3 equations, we have 3 variables. This is a little different than just combining or using substitution. And so sometimes we have to think a little strategically on how we can use one of the equations twice. And this is really important because we have 3 equations to keep in mind. So it's important that we work with all of them and make sure that one of the equations works with both of those equations. Eventually, we'll be writing our answer in the following term or following setup, where x, y, and z is considered our solution. So with this, using elimination to solve this system seen here, a good rule of thumb, and I think good questions to ask are, can I eliminate anything already? Meaning, do I see any variables that could already be eliminated? Hopefully you're noticing that we could combine equation 2 with equation 1. So how I'll go about this, I know that if I combine equation 2 and equation 1, my z term will cancel. So how I'm going to denote this is by saying if I were to combine equation 1 and equation 2, that would get me here to 3x plus x, getting us 4x. Y plus 2y, getting us 3y. Z term cancels, notice, that's what we wanted. 1 and 4 would get us 5. So notice that we've just worked with the first 2 equations. And now, do we see any other variables we could eliminate or anything else that we could modify? Hopefully you're saying that we can also eliminate the z variable if we combine equation 2 and equation 3. So if we go from there, combining equation 2 and equation 3, leaving us with 4x, we now have 1y. Our z term canceled because that's what we wanted. 4 and 3 gets us 7. And so this has simplified the problem immensely, although it seems like we're just stuck now and we don't really know necessarily where to go from here. This should look like a problem that we've solved previously. So I know that we don't have any opposite coefficients, so we definitely have to resort to a linear combination. Because if we can solve for x or y, we can definitely solve for x, y, and z, just based off of the fact that we've simplified this to two equations. So how I personally would modify this is by going about and multiplying equation 2 to try and eliminate this x term. I would go about and multiply it by -1. So if I rewrite this, I still have equation, or this first one, 4x plus 3y equals 5. But now I have -4x minus y equals -7. If we combine from here, 3y minus y gets us 2y. 5 subtracting 7 gets us -2. So our y term is definitely -1. And so a question, how can we go about solving for our x term? Well, we already worked with a system of equations. I think the biggest part here is just seeing how you can combine these three equations, making sure that one of the equations works with the other two. That's really important. So you can pick your poison. So now we're solving for x, where we know that if we took 4 times x and we added on y, this equals 7. But now we know that y is -1. So if we have 4x and we're adding on -1, this equals 7. We can get rid of this by adding 1 to both sides. 4x equals 8. So x is going to have to be equal to 2. And then you might be saying to yourself, how can we solve for z? Because we've solved for x, we solved for y. How can we get z? We're lucky enough to have these three equations here, so you can really pick your poison. So if we solve for z, I'm personally going to go about using equation 2 because all of these terms are positive. Positive x, positive 2y, positive z, positive 4. That'll make my life easy, I think. So if we plug in accordingly, we know that we have x plus 2y plus z equals 4. X equals 2. We're adding on 2 times y, where y is -1. And we're adding on z, our final variable that we have to solve for. 2, and we add on this. It's pretty much 2 minus 2 plus z equals 4. These 2's cancel. So we're just left with z equals 4. If we go for our final answer in the format that they mentioned at the top as an ordered triple, similar to an ordered pair, but now we have 3 terms, so it's an ordered triple. We have x is 2, y is -1, z is 4. And this is our final answer. So we have one unique solution. That's something to also point out on. Just one. Eventually, if you end up taking linear algebra in college, you'll be able to see that when this is all simplified just based off of coefficients, the terms on the right-hand side ended up as our x, y, and z term. So eventually, if you take linear algebra, you'll be able to solve these even quicker on a calculator.